All right, so we're going to go through and just work the problems out together. And here's the first problem. What does this print on the console? Well, look here. There's only one variable involved here, so all we need to do is keep track of the state of I. So first we set I to 0, and I'm going to do that right here. I'm just a little side note here. I is 0. And now we enter in the loop, and we compare 0 to 7. 0 is less than 7. And so we multiply 2 times 0 to get 0, and then we print it. So we're going to print 0. Just going to go to the new page there. And then we increment I. So let's increment I. Now I is 1. And then we do the loop test. We compare I to 7. 1 is 1 less than 7. That's true. So we continue with the loop. So 2 times I, that's 2 times 1, that's 2, and we print that. So that'll be 2. Actually, the computer's going to print this. We're not putting any spaces there, but I don't care about that. You could put a comma or space. It's all right. And now after we print 2, we're going to increment I. Now I is 2. And then we'll compare 2 to 7. 2 is less than 7, so we print 2 times 2. 2 times I is 2, so that's 4. And you can see the pattern here. And now we're going to increment I. We're here. So I is going to be 3. And obviously we can kind of carry out the pattern at this point. We're going to print 2 times 3, that's 6. We're going to increment I, it's 4. We're going to print 4 is less than 7. We're going to print 2 times 4, it's 8. We're going to increment I, it's 5. 5 is less than 7. 2 times 5 is 10. Increment I is 6. 6 is less than 7. So we print 2 times 6. This is where we need to slow up a little bit. We print 2 times 6. Now we increment I. We go in slow motion now. We get 7. We compare 7 to 7. 7 is not less than 7. That's false. So we end the loop. The next statement that we execute is the one just beyond the closing bracket, and which is not shown here. So that's it. Those 0 through 12, even numbers. Rewrite the code in figure 1 so that it uses a for loop. Almost everybody got this. I'll do it quickly, but it's essentially everybody got this one. So for, and we put the initialization, actually we get the whole thing in there, put this initialization in here, and we have the test in the middle, and then we put our increment operation in here. But we don't use a comma, we use a semicolon here. We don't need that there. There's number 1 written as a for loop. Here's number 3. How many times does the body of the for loop run in the code that appears in figure 2? How many times does it run? Well, here we have to think about what I is being set to. So I is first 0. And actually look at this, k doesn't change. K does not change. So this is essentially equal to this, that loop. This k is not varying in the problem. So if we start at 0, and we test to see that whether I is less than 100, and then if that's true, then we increment I. Well, we do this and then we increment I. How many times does this loop run? Well, you can just imagine this. Imagine printing I. So we're going to print 0, and then we're going to increment I, and then we test to see if I is less than 100. Remember, the plus plus I, that third component in that for loop, is done at the end of the loop, on the inside of the loop, at the end of the loop. So this cout will run for I equals 0, it'll run for I equals 1, but will it run when I is 100? Remember, I plus plus happens at the bottom of the loop, which is after we print this. So when we do plus plus I, and I becomes 99, sorry, let's suppose I is 99. Let's suppose that we just finished the end of the loop here. I don't know if I can explain it like that. Let's suppose we print 99. I is 99. Okay, we printed 99. That means we printed, so far, we printed 0, 1, 2, like that, all the way to 99. So we printed 100 numbers. So we print 99, and then we add 1 to I. So I becomes 100. And then we evaluate the condition. 100 is not less than 100. So we do not continue executing the body of the loop. So we're finished. So the answer is 100 times. The loop runs 100 times. Because the trick is the counting starts at 0 and ends at 99. If we shifted everything by 1, we'd start at 1 and end at 100. This, by the way, this is called, to get this problem right, it falls under a category of problems called the off by 1 problem. And it's so common to be off by 1. So when you're analyzing algorithms or procedures that involve counting, it's typical to be off by 1. You have 1 too many, 1 too few. You're not sure if you got exactly what you need there. So there's an off by 1 problem. All right, what about this one? This one I thought was the hardest problem on the test. What does this code print to the console? Whoops. Let's break that there. What does this print to the console? So, I mean, you'll have to attack this in all different ways. I don't know how I would solve it right now, but I'll think through it. Let's think through it. So, we have to pass through this loop before we get to this cout. So this is the only thing that prints something to the console, and this is not inside the loop, it's outside the loop, so it only runs once. So the problem is to figure out what I equals when this statement executes. And we start with I initialized to 11, and then we add 3 to I until I is greater than 99. When I is greater than 99, we exit the while loop and then we print I. So that means I is going to take on values that look like this: 11 plus, say, k times 3. So let's think of, let's look at some examples. Let's see, if k was, say, 20, it'll be 11 plus 20 times 3 And what is that? That's 60 plus 11, that's 71. Okay, well, we're still under 99. I mean, we could set this up to solve an equation. That's what some people did. But I'm going to do it in a way that doesn't, that I think is a little easier. What if we made this 30? That's 90 plus 11. That's 101. But 101 is too big. Well, it could be 101 actually. Because 101, if I were 101, we would exit this loop and print 101. But do we make it to 101? I don't know. Let's go to 29 here. This is the value that I takes on. Do we make it to this number? Well, this is 98. I mean, it keeps 71 there, by the way. Let me go backwards here. This is just for the record. This is 101. Well, what about what about 29? I'm not going to bother to do 3 times 29. I'm just going to subtract 3 from 101. So that's 98. If I is 98, do we execute the body of the loop? Yeah, we do, because 98 is less than or equal to 99. So when we do this, we now reach 101. And 101 makes this expression false, which means we execute this line and we print 101. So the answer is 101. Any questions on that one? I thought this was the hardest one, but I don't know, maybe it wasn't. And this one, there's generally good results on this one here. This is the integer. This is the problem that checks to see if you know how to distinguish between integer division and floating point division. So when we're doing the division operation, if both arguments are integers, then the compiler interprets division as integer division, which means it throws away any remainder. And it doesn't do any rounding. It truncates. So if you got 9.999, you're going to get 9. You're not going to get 10. So 1 divided by 2 is 0, because 1 divided by 2 is less than 1. So the remainder is, we get 0 with a remainder of 1. What about, then we print a comma. Actually, if you didn't put a comma in there, it wasn't a big deal. What about 1 divided by 2.0? Here we're using a decimal point at one of the constants. So that's a signal to the compiler that we want floating point division, not integer division. So the result of this division is a floating point number. We're going to get 0.5 or 0.5. All right, let's look at the next one. Question?
1 divided by 2.00, would that change the accuracy of the decimal?
No, we'll get the same result there. Yeah. All right, let's do 6. Okay, this is a test to see whether you know the difference between postfix or a post increment or pre-increment. And this is the post increment, and this is the pre-increment. Pre-increment means evaluate to do the increment and then use the result in the expression of which it appears. The post increment means use the variable in the expression of which it appears, and after you're done that, increment the variable. So we'll need to study the state of I and K, I believe. Let's see, I is initially 2. and k is set to something times 2. And we know that after this something is evaluated, I will certainly be 3. But do we use I in its state of 2 in the multiplication, or do we use I in its state of 3 in the multiplication? Which value for I do we use when we do the multiplication? So this is post. It comes after the I. That means we delay the increment. First, we use I in the expression in which it appears, and then we increment I. So let's use I within the expression in which it appears. So I is 2. So that means k will be 2 times 2, which is 4. And then we have to increment I. Right? We're incrementing I. All right. Now let's go to the next expression. Well, we have this to do. We need to evaluate this expression and then print it. Well, to evaluate this expression, we first need to evaluate this expression, right? Because multiplication has higher precedence than addition. So we do the multiplication first. And in this case, we have the pre-increment operator. That means we need to increment I before we use it in the expression in which it appears. Let's increment I to get the job done. Get the job over with. I is now 4. Now let's use 4. Let's use I, which is 4, in the expression in which it appears. Actually, I'm going to do it like this. So it'll be 4 times 2 plus k, which is 4. And that's the same thing as 12. So the answer is 12. Sorry. Any questions on this one? Question?
How is I4? Sorry, I missed that.
How is I4?
Yeah.
Is that we have to increment I before we use it. I was 3. I was 3 because we set it to 2, and then we increment it. Now it's 3, and then we increment it again, and now it's 4. Okay. Write a C++ program that computes the sum of n integers. So we need a variable that accumulates the sum. So we'll declare it like this. Some integer sum, and we set it to 0. We have to initialize it to 0. And we have a value n. We need to add the numbers between... Oh, so we rewrote this question, didn't we? Write a C++ program that computes the sum of integers 0 through n. Something like that. We rewrote that question on the board. So we need an accumulator. So that's what we declare this variable called sum. That's an accumulator. We're going to accumulate the numbers. So we're going to do something like this. It's going to look like this. We want sum is 0, and then we want sum is sum plus 1, and then we want sum is sum plus 2, like this, see? And we just keep going. Whoops. Sum equals sum plus 3, all the way up to n. And then maybe we'll do something, although you didn't have to do this, but just to make it more understandable. So this is what has to happen. So we set sum to 0, we add 1 to it, then we add 2 to it, then we add 3 to it, like that. So we have to do this addition n times. So let's use a for loop. And we can do it this way. So we range from 1 to n. So we let I range from 1 to n. And then whatever I is in each of those cases, we add it into our accumulator called sum. So the whole answer would look like this, right there. There's the answer. We declare sum. And you don't have to do int sum, although to get it to compile and run, you'd have to do that. But you don't need that. But I wanted to see the initialization of sum to 0. That's an important part of the problem, important part of the logic. Any question on this one? And we might want to print it as well, though this is good enough. All right, let's do the next one. Write a C++ program that prints every number between 330 and 550. So there's many ways of doing all of these problems, but I'm just going to show you what I think is the easiest. So once again we need some variable that's going to range across these values, 330 to 550. So when we output this thing, it's going to look something like this. Right? And we start by printing 330, then we add 1 and print 331, then we add 1 and print the next one. We keep adding 1 until we print 550. As soon as we print 550, we're done. So let's start with I equal to 330. So I is going to be less than or equal to 550. See, because here we're going to do this. So when I is 550, I want this condition to be true, so that I print 550. Because we use this word inclusive here. It means I want to print 330 and I want to print 550 both. We need to increment the counter. Any questions on that one? Okay, suppose that a program prompts the user to enter a number between 3 and 12 inclusive. Suppose the program stores this value in a variable named x. Write code to check that the integer is in the range 3 to 12. So we have a variable called x. So if x is greater than 3, greater than or equal to 3, because this is in the range. So you know these square brackets mean inclusion, right? So 3 and 12 are included in the range. And x is less than or equal to 12. You can do anything you like here, just whatever you want. This would, if you gave me this answer here, I'm happy with that. That's all I wanted was that. Well, if you put in like cout, good number, and have an else statement, bad number, that's all right too. You could do that as well, but this would be a minimum answer. All right. Question on that one?
Can you answer number 9 using a for loop or not?
No, there's no, well, no. What if x is a floating point number? How are you going to use a for loop with a floating point number? So we don't say it's an integer here, right? So if x were an integer, then we could use a for loop to check, does x equal... I still don't see how you can use a for loop. I don't see how you can use it. Do you want to suggest that? I don't. Even if x were an integer, I don't see how to use a for loop there. You don't want to analyze your for loop?
No, I asked for the user to enter a number, and
Yeah.
I got the number and I put it into a loop.
Well, let me see your paper. No, that's not quite it. Yeah. No, you put the conditional inside the loop. Maybe that's good for some. Let me give you a partial credit on that one. I think you got the concept that I was looking for. See me after class with that paper, okay? All right. All right, let's do this one. The code in figure 6 prints odd number when the user enters an odd number. Rewrite the code so that it prints even number when the user enters an even number. So it's that one is pretty straightforward, I think. And just change this. This prints an even number because this prints odd number because we take I, we divide by 2, and we toss out the answer and keep the remainder. So we take I, we divide by 2, and we get the remainder. So if I were 3, we would do 3, take out 2 with a remainder of 1. That would be true. That's why 3 is odd. Look at 5. 5 divided by 2 would be 2 plus a remainder of 1. So that's also odd. But if it were 4, then 4 divided by 2 is 2. It goes in 2 even. So the remainder is 0. Just say so. All the odd numbers return a remainder of 0. So it's just the other way, right? So this operation, an integer mod 2 will only return 0 or 1. Because the remainder has to be less than 2. And if we did something like this, let's suppose we did x mod 3. So this will be in the set 0, 1, or 2. So the remainder is going to be either 0, 1, or 2. And if I mod 4 is the same thing. So we'll never have a remainder of 4. If we divide by 4, we're not going to get a remainder of 4. And we're not going to get a remainder of anything above 4. It's 0 to 4 minus 1, which is 3. So for even numbers, the way to detect an even number is you divide by 2 and check its remainder. It's got to be either a 0 or a 1. If it's a 0, we know it's divisible by 2. That means it's odd. I mean even, rather. If it's if a number mod 2 gives 1, we know it's odd. Any questions? That's it.